Hello. So today we start a new chapter, chapter number 4, moving charge and magnetism, class 12 physics. So moving charge and magnetism. Okay. So previous chapter we studied the electric field, okay, and the electrostatic force and electric field. Okay. So there is a charge in previous chapter. The charge is static. Charge is static means the static charge create an electric field. So static charge create an electric field. Okay. Now here the name suggests the moving charge. The charge is now moving. So moving charge create a magnetic field. Create magnetic field. That's the very important concept. Okay. So the represent that B, and similar as electric field, there is a vector field. Okay, so electric field and magnetic field are both is very important in our daily life. Okay, because the Maxwell proposed the unified field theory. Mainly the Maxwell proposed the unified field theory means there is a two field, electric field and there is a magnetic field, both combined together to get electromagnetic theory. Magnetic theory, as that are very important in our daily day communication in life. Okay, because the mobile communication, the telecommunication, satellite communication are related to that the Maxwell equation, the very important Maxwell's equation and that Maxwell's electromagnetic theory. We can't ignore that. So that's why the magnetic field and electric field both are important. And we know that what is electric field, how to generate electric field. There is a basic calculation electric field and force. Here we study what is magnetic field. Okay, how the force related to the magnetic force related to the magnetic field. Suppose there is a charge, say the charge is moving. So charge moving in conductor, where okay, the charge there is called electron or a proton moving in a conductor. So there is a dq amount of charge moving in a conductor with respect to some time. So we get current. So moving charge here, the moving charge create a current. Moving charge with respect to time create a current, and that current passing through that wire I create a magnetic field surround that wire. That current create a magnetic field surrounding that wire. That Hans Christian Ørsted, the name scientist is Ørsted, in 1820s, when he take a class, okay, he noticed a current passing through a wire, there is some deflection in magnetic compass needle. Okay, so he conclude that the moving charge produces current and that current generating magnetic field. Okay, but mainly magnetic field generating by the current. Magnetic field generating by the current. By the current. Okay, so here the concept is clear. So Ørsted notice there is a current direction. First we conclude what is a current direction. There is a two direction here. So there is the cross and that is a dot. So cross direction I will describe that. Take an example. There is a person A throwing an arrow to person B, and that's a vectorically. And when a person A see that arrow, so just see the cross part. So cross path means when I see that cross path is my from respect to me, when I see that a cross means the current is towards board or into the board in the current direction into the board. Or B person C, there's a dot, there's a tip point of that arrow is a dot. When I see that dot with respect to me, or I see that a dot here means current I is leave the board and towards me. Leave the board and towards me. So here the important is towards me. Okay, so I'm going to leave the board and towards me. That's my case. Okay, towards me. So there is a two direction, and from similar that vector concept here. There is a two current direction into the board or towards observer. Okay, so now O state describe where current passing through that wire produce a magnetic field. And now suppose there is a cross and there is a dot, produce a magnetic field. Okay, now put a compass needle, magnetic compass needle, place here. Okay, place here. So magnetic field is a vector field. So direction is very important. And so here that these are compass needle, and compass needle there is a north pole and compass is a south pole, and this north pole aligned to earth south pole, because we know that like poles they repel and unlike polar attract. So that's why north polar south pole they attract. So now the important is that what is the direction of the magnetic field. So we know the current direction into the board, and what is the direction of magnetic field. And when you find that direction of magnetic field, there is a two rule. So both are similar, the right hand thumb rule or a screw rule. The two rule is right hand thumb or screw. So right hand thumb states there is a thumb, okay. The thumb represent current, and curl of other four fingers that's rounded, like starting from to ending, the curl represent magnetic field B. Similar to the screw rule, there is a screw, top part of the screw. Okay. When I rotate in clockwise direction, when screw rotate in clockwise direction, right hand screw, the clockwise direction, the direction is that magnetic field. And the screw goes towards the wall in that direction. So that's the current I. Okay, or move the anti-clockwise direction in that direction. Okay, so screw is outward from the wall, so means that the I. There is a two rule, right hand thumb rule or screw rule or right hand screw rule. Both are satisfied that magnetic field direction, and you know that the field starting from north pole ending towards south pole. So here there is a screw or a choose that is a right hand thumb rule or a screw, means you see that that's the current into that whiteboard or into the wall. If I choose that board, this whiteboard be a wall, and this current goes into the valve, means the screw into the valve. So there is a clockwise direction. There is a clockwise direction. Or put a thumb here. A thumb represents the eye into the wall or into the whiteboard, and rotate that, we get a clockwise direction. That's very important. There is a clockwise direction. So that is here the north pole, here the south pole. The south, that's the north. South, that's the north. Clear? Now, similar that eye, there is a circular. I put a magnetic compass here. Okay, the screw or a finger outward from the wall. So there is a anti-clockwise direction B, vector, that is the B. So that is the north pole, that is south pole, south, north. There is a north to south, that is a north. Okay, that's very important. Clear? How the current and magnetic field are related? Okay, that's very important. So we get magnetic field. Okay, so current passing through the wire means a moving charge, means moving charge with respect to time create an current. So magnetic field is generating by that current. So the current is passing through the wire, generating magnetic field. Okay, surrounded space here. Now the another important concept, or taken another example, there is a tabletop. There is a table. And we put some iron dust here. Iron dust here. A very small iron particles. These iron are the magnetic material, obviously. And there is a current where connected to the battery. When when the current passing through the wire I in that direction, from whole and in that direction, we see that right hand thumb rule. So, like a tabletop, we put a thumb here, and you see that there is an thumb, means that the out of the this tabletop, that's a anti-clockwise direction. So this iron dust or iron particle arrange some this circular path, not in arrange normally. They arrange in this circular path. Okay. Now there is a direction, very important. The towards there is a clockwise. That's the magnetic field B. That's the current I. Okay, both actually satisfy the right hand thumb rule or screw rule, or to satisfy the magnetic field and current direction. That's a very important. So another important point is there is a force related to that. Like a static charge create an electric field. So there is a force, that is electrostatic force. Similar, there is a magnetic force. Okay. So now when taken another example, there is a magnet here. Suppose that is a north pole, that is a south pole. So magnetic field in the left to right, north to south. Now we put a where? Suppose we put a cross. So means current in that direction I. Okay. So B in that direction. So there is a force. Okay. And that force is related to I cross B. The force is related to I cross B. So that is the I cross B means the force is downward direction. Okay. Now if you say that the current in that direction I, B be the same obviously in that direction. So I cross B, so we get cross B, so that is the anti-clockwise direction, so force is upward. Okay, so there is a force, that's a magnetic force related to the current cross magnetic field. That's very important. Okay, now take another example for a better understanding. There is a wire, suppose to that is a wire. Current in that direction, left to right direction. So that current produces a magnetic field. Okay, and here the magnetic field produced by that magnet, and here the magnetic field produced by that current wire, current passing through that wire. So that's the in that direction. When I that's the in that direction. So that's the these. Okay, for screw. Okay, when someone moving the screw, so in that direction, so in that direction screw. If I see from here, someone standing from here, the screw, if I see that's the left side, so right to left, so that's the anti-clockwise, so current is out from that towards that person. Okay, so let's ignore that, and that cross represent the magnetic field. Now put another wire in that portion. Okay, that's current I1, there's the current I2. If both are in same direction, so there is a magnetic field generating here, there is a dot here. When both current are in same direction, so these current would generate magnetic field here, and these current passing through the wire generate magnetic field in here. So this magnetic field in that direction, here the magnetic field in that direction. So that is a B, that is a B, current direction is I, here the current direction be the same I. Okay, now there is a force, the force equal to I cos B. So I cos B, so we get, okay, there is a clockwise, so downward direction, the force is downward. Similarly, that's the cross I cos B, that's the anti-clockwise direction, so force is upward direction. So when the current passing these two wires produce a magnetic field, and there is a force, and that force is towards each other. Okay, this force is towards each other, then that wire slightly goes in downward direction, and these wires slightly go to upward direction towards each other. There is a force. Okay, now if I change the direction of the current, suppose if I change the direction of the current, suppose I say now there's a I1, I2 be the same. So I2 be the same in that direction, I2. Okay, so I2 generate magnetic field due to I2 here in I1, and the I1 also generating magnetic field. Okay, so I1 also generating magnetic field in here, in that way. So magnetic field in dot, these dots are generated by I1 wire and I1, and these dot magnetic field generated by I2, because the current passing through wire generate a magnetic field, and these are magnetic, both are in dot in same direction. Now that current direction are the different, so that is a I, here the direction is I. So we know the force is I cross B. Okay, so I cross B, that is the anti-clockwise direction. So force is, okay, upward. I cross B, force is upward direction. Now here I cross B, now that is a clockwise direction, and that force is now downward direction. So means if both current are in opposite direction, so they are the force, now they repulse. So this wire goes upward, where goes upward, and that's the wire goes downward, goes and towards each other, where goes each other. There is a force. Clear? How they get that? Now, how to calculate that force, that magnetic force, a B? That's an important concept, that the electrostatic force, we know that they create a static charge, that static charge create a electric field, that is a Q times electric field. Similarly, if I calculate the magnetic force AB, create a magnetic charge times magnetic field. Now another a question arises. So is it true? No. Why? Because that Q, okay, there is single charge. Here there is a monopole, no magnetic monopole. There is a no magnetic monopole. There is always dipole. If someone try to interested to discovery of magnetic monopole, then this equation be true. Otherwise, there is no magnetic monopole towards that time. None other than any one person can try to invent the magnetic monopole. So that's why we conclude this equation is wrong. When someone is invented and satisfied that the magnet has monopole, then equation is true. Otherwise, this equation is wrong, because magnet has no monopole. Okay. Now is another concept. So what is the value of AB now? If I say that this equation is wrong, so what is the correct equation? So there is a charge Q, that's the velocity V. So there is some velocity, suppose consider there is an called electron moving in that direction. So current moving in opposite direction, I. Okay, and there is a produced a magnetic field. Now it's very important, there is a magnetic field, and what is the direction of the magnetic field? Okay, so now I suppose stand here, so I see that the current is away from me or towards the board. So towards the board means if I towards the board, so that is a my left side goes up, right side goes down. Okay, or the screw moves that my left side goes up, right side goes down. That's the this direction B. Or I stand in front of that where means the current is towards me. So that means my right side goes. So my right side now change into my left side. Right side goes up. That's the correct. So my right side, okay. So my right and left there is a changing. That's why the B is in that direction. Okay. When a current is in front of me, okay, my left side goes down, my right side goes up. That's my left side. I choose that front. I here that's my right side, that's my left side. Okay, so my left side goes up, right side goes down. When you put stand here or there, both are in same direction. Okay. Now that's very important. The B direction. So that's now a force. Very important concept. The force, that's a magnetostatic force. The AB by magnetic force is perpendicular to velocity. So force is a perpendicular to velocity. How to find that? And you see that the current passing in that direction. So either moving a proton or moving an electron in that direction. So force is always up. Or same case here, the current move these proton move in that direction, so electron move in that direction. You choose any of the particle. So force is always perpendicular to that velocity of the charged particle, and that force is directly proportional to the velocity. Is more velocity you get more force, less velocity means less force. Now here AB similarly is directly proportional to charge Q. Okay, so here that the AB, the magnetic force, that is equal to Q, the charge, that is V cross B. V cross B. That's the final answer. And I will see that there is a V cross B, we get final answer, that the force here. Very important. Now we combine these two, the electrostatic force or magnetic force, combine these two. If electrostatic, if EL plus FB, F total, that is a Q times E plus Q times V cross B, Q common, so we get E plus V cross B, and that force is another name is called Lorentz force. Lorentz force. Okay, clear. So there is a B is a magnetic field. That's very important. So what is the SI unit of magnetic field? So from this equation you know what is the SI unit of magnetic field. So force is that a Newton by Q is a coulomb. There is a velocity, by velocity means meter per second. So Newton second by coulomb meter. Another name is called Tesla. The famous scientist Nikola Tesla, the name is come from the Tesla. So here the 1 Tesla equal to 1 Newton, 1 second, 1 coulomb, 1 meter. And Tesla is a very strong magnetic field. Strong magnetic field. Magnetic field. Okay. So another unit of magnetic field is called Gauss. It's not a SI unit. SI unit is a Tesla. So 1 Gauss, that is equal to 10 to the power minus 4 Tesla. That's the SI unit. Clear? What is magnetic field? Okay, and how magnetic field related to that magnetic force. It's not a similar exact like that electrostatic force. There is some difference because that charge is static charge. Here the charge is not static. Here the charge is moving. Okay, so force related to the magnetic field similar that electrostatic force. Okay, now there's a basic concept of what is a moving charge and what is a magnetic field. If any doubt in that section, always ask in comment section. I will try to give the answer. Next class we discuss more about that magnetic field and magnetism. So today in the class here, if any doubt, always open in comment section. Thank you.